Alright guys, today's the day. This is part 3 of how to implement the fast Fourier transform or FFT for audio programmers. In the last video we made this function called solve DFTR for recursive, in which we could solve for a particular bin's DFT in n log n time. We figured out that n log n algorithm in the video before that, so if you haven't seen this one, go start this series from the beginning. Because this is super, everything builds off of the last video and videos before that. So yeah, today we're going to jump into how to actually make the FFT, which does not take in any particular bin frequency, but it finds all of them. Alright, so I'm going to start by getting rid of all this other n log n stuff we did before. And I'm going to create a new function called FFT, and it's just going to take in coefficients, and then I'm just going to copy everything from solve DFTR, because that's going to be our starting point. Okay, so with our starting point, we have to do one thing first. So basically, this is fundamentally changing. We're not returning a value, we are returning an array. And not just a single array. We're containing an array of arrays. We're containing an array with both the real and imaginary parts of the Fourier transform for each bin frequency. So before we were just returning, as you can see over here on the left, an array of 2 values. This is for the particular bin we specified. Now we're going to return an array of a bunch of these, right, for each bin. So what that means is, first off, in this recursive part, we are not going to be returning particular one of these. We're going to return a list of coefficients and a list of 2-dimensional coefficients, which means this will return an array of arrays. So we're no longer going to return the first element of this. Right? The second thing is I'm not going to make this, well, I'm not going to make the same mistake. I'm just going to get rid of this. We're calling this function recursively, not another function. And thirdly, we don't need this because we're solving for all bins, not one in particular. Right? Okay, so now, instead of solving for x here, we are going to solve for all bins. So we'll be doing this particular part right here for all bins. And we'll replace this with I, right? Okay, cool. What's next? Well, here's what's going to happen. We're going to essentially concatenate these even and odd arrays, right? We're going to get down to where we did before with the single elements, but we're not going to return single elements. Basically, we're going to concatenate the Fourier transform, and slowly we're going to build back until we have all of the bins back, which means that we're not going to be returning a static 2-point array. We're going to be returning bigger and bigger arrays until we get back to the original size. So that means we need a new variable, which I would call FT, which is an array, and it is going to contain all, for each recursion cycle, all of the Fourier transforms of the bins. So in JavaScript, I go push new float 32 array size 2, right? Because there's a real and imaginary component, 2 components. All right, cool. Just for debugging, I'm going to go ahead and console.log this. So, and we're going to return the result, right? All right, so now we still have omega, but we are And hopefully you can see and my camera's not obstructing the code. I'll try not to work like that. But instead of real and imaginary value being variables we return in the recursive cycle, since we're in this for loop, we are going to, basically this will be the real and imaginary components of FT of I, which means that I'm going to do this. And this is the real component, so it is 0. And this is the imaginary component, so it is 1. And now for each even value, we also need to index it because it is also a double array. Alright, so we're going to run into this error here saying cannot read properties of undefined reading 0. Well, that's because if you think about it, both evens and odds have a length of n over 2, and coefficients has a length of n, right? Because there are n over 2 even and n over 2 odd elements inside an array of size n. So that means that we actually have to use our for loop only through half of the length. But that doesn't sound right, right? Because we're not getting all the bins if we do that. But let's go ahead and just say this. Our length over 2. So why do we have to do that? Whoops, I called it results. It's really FT. Well, this isn't the right answer, right? But that makes sense because we're not going through all the bins. So we're only going through up to length over 2 bins. But how can we do this, right? We seem stuck. How can we somehow solve for the remainder of the bins? We don't have anything with evens and odds for higher than length over 2. Well, here's what MS Paint is for, to save the day, right? This is what we're gonna do. Whoops, I have a weird component on. All right. All we need to know is that to get to the other side, let's say this is us, right? To get here, all we have to do is just negate x and y, right? To get here. And you can think of this as being sort of the up until this is 0 here. This is, I'm sorry, theta is 0. And then this is theta is equal to, right, pi over 2, but this is really bin 0 and bin n over 2, right? So if we want to get further bins, you just have to negate the x and y values, and that's what this bin will be equal to, right? It's just got the negative x and the negative y components. It's just trig, and here's another visual intuition on a wave. That's all we have to do, guys. So since we know that, it seems surprisingly easy, but it's a simple trigonometric property. We just have to add a length over 2 to these, and then subtract the same thing that we had over here. So instead of plus, as you can see, it will just turn into minus. And I'm going to close this up. And now let's open this up again. And as you can see, we have finally our fast Fourier transform. And if you don't believe me, here you go. Everything is in alignment. Wow, guys, so this is it. We have officially created our fast Fourier transform. This is quite cool. Hopefully through this little series you have you understand now how the fast Fourier transform algorithm really came to be. I believe this is the radix 2. I believe that's what you call it because we're using evens and odds, right? It's a power of 2. But There's a lot of research you can do. I've done a lot of research on the web. I feel like my series gives a very unique and hopefully like intuitive look of how this stuff really came to fruition. And hopefully you have the knowledge now. It's not such a mystery how the fast Fourier transform came to be, right? Because we have just implemented the fast Fourier transform, at least forward, right? I mean, going backwards is going to be trivial. I'll do it in a little bit in maybe another video. And I'll also work on refining and optimizing this algorithm. But I've just showed you the basics for it. And from here on, hopefully you can figure some stuff out on your own. But that's basically it for the main part of the series for how the algorithm came to be. Everything from here on out will be how we can optimize the FFT and make it a little quicker in many cases, and how we can make it in place, which is a huge time saver, and makes the code a little nicer for languages like C and C++. But anyways, yeah, I hope you guys really enjoyed this little series. Please let me know if there's stuff you don't understand, or if you liked it, or if you didn't like it. And yeah, thank you for watching, and stay tuned for some other videos. But just a reminder, I will be making more videos in this series, but at this point, I've showed you how the fast Fourier transform works. So yeah, thank you for watching.